Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Olalo and I'll be guiding you through the chemistry course. In this particular lesson, we'll be looking at the organic chemistry 1, the part 1 of the organic chemistry. This is one very interesting part of chemistry that you don't want to miss out of. Alright, in this lesson, we'll be looking at what is organic chemistry, what is it about, what are the characteristics of what are the characteristic features of organic compounds. I'm going to define some terms in organic chemistry. Then we'll look at how the IUPAC nomenclature for aliphatic compounds, how they name things according to the IUPAC standard. Then we'll look at stereochemistry, after which we discuss the classification of organic compounds. We'll look at hydrocarbons, then we'll start talking about alkanes, alkynes, alkenes, alkynes. Of course, we'll talk about the intermediaries. The first of them, that's methane, ethene, and ethine. And then we'll look at the aromatic hydrocarbons, where we'll discuss benzene. Then we'll go to alkanols and close with ethanol. Alright, let's get started. Organic chemistry. When we think about organic chemistry, all I want you to picture in your heart is simply the chemistry of life. The chemistry of life. Well, when we use the word organic, it means it has to do with something that is closely related to life. So this chemistry actually has to do with a lot of compounds, a lot of interesting things. And organic chemistry has some major features that are common to them. One of the major things is that it is majorly the chemistry of carbon. Is majorly the chemistry of carbon. That is the major component in most of our reactions, in most of the things we'll be talking about, is carbon. Also, you'll find out that apart from carbon, you will see hydrogen, you see oxygen come to play. So they too have their own individual roles in the organic chemistry. Apart from the carbon, hydrogen and oxygen, other substances such as silicon, nitrogen, helium, all of them, every other element can come to play one or two other parts in organic chemistry. So we don't see those other ones so often. We don't see them so often. But what we see almost always is the hydrogen, the carbon, and the oxygen. So let's look at some of the characteristic features. Some of the characteristic features of the organic chemistry. Now we notice that carbon has some specific attitude. Apart from the fact that it is carbon and hydrogen and oxygen that are the major components, carbon has the potential to connect with other compounds, with itself and other compounds, that is, to replicate itself in connection in a very long chain. It has the potential to connect to itself in long chains. So because of this connection that it makes with itself, it leads to something we'll talk about much later, which is polarization. So this polarization is one of the reasons for which we describe this particular aspect of chemistry as organic chemistry. We actually do study large compounds. Compounds so large, one particular compound that is so big, larger than expectation. We can see about 500 millions of compounds of carbon atoms connected to each other on a straight chain, on a curved chain, or any kind of chain. This is only found very much in organic chemistry. We also notice that apart from in straight lines, we also see them in curves, in circles. We also see them in different kinds of shapes. In fact, in organic chemistry, you can have a particular compound with different names based on the arrangement, the structure of the substance. So, organic chemistry, here we go. Alright, before we go deep into organic chemistry, let's take some terms of some terminologies that will be used in organic chemistry. About now, you should have definition of some of the terms on your screen, and the first of them you have there is homologous series. The homologous series. The homologous series refers to the family of organic compounds which follows a regular structural pattern. That's the homologous series, is a specific family, the pattern that a particular family follows. We also talk about the alkyl or the functional group, the alkyl group and the functional group. The alkyl group includes all groups that are derived from alkanes by loss of an hydrogen atom. A functional group is an atom, a radical, or a bond common to the homologous series and which determines the main chemical properties of the series. So we see what we're saying. We talk about homologous series, that's the ending of each of the substances. Well, we have not started looking at the substances, but on your screen, right, you see some particular structures that are being drawn there, where we'll be seeing different kinds of homologous series. We have the alkane, the alloalkanes, the alkanol, the esters, the alkana, and the rest of them. We see their formulas there. Also, we can decide. We'll have to talk about saturation of a particular hydrocarbon. Saturation of a particular hydrocarbon. If we have, we know carbon has 4 valence electrons, as 1, 2, 3, 4. Now, a particular carbon atom that has all its valence electrons occupied by either an hydrogen or another carbon, another structure, or better still, even if it is going to have a carbon, should not have more than a singular bond. A single bond between the carbon and whatever it is connecting to is said to be saturated. It is said to be saturated. So when we talk about saturated hydrocarbons, we'll talk about the alkane group, which because they actually form structures something like that. And we don't say a particular this thing is unsaturated. It means it has more than one bond connecting between 2 carbon atoms. It has more than one bond connecting between 2 carbon atoms, as in the case of ethene and the rest of them. That's in this particular case, and of course it can also be something like this in ethyne. Of course, we're coming to ethene, ethyne, and the rest of them. What other term do we need to clarify? Of course, we've seen the carboxylic groups. You've seen the groups, the functional groups. Mentioned ethene, the ethyne, the alkanols, the ethers, and the rest of them. Also, it is good to also know the general formulas for each of the functional group. The general formula for each of the functional group. When we'll be working with them, we'll be having general formula for each of the functional group. This general formula is simply an expression that shows the number of components, number of each of the components that can be found in any of the substances of that particular group. For example, we'll talk about general formula for alkanes. We say alkanes generally is CnH2n plus 2. CnH2n plus 2. We'll talk about alkenes to be CnH2n and alkynes to be CnH2n minus 2. So all this, they have influence, they have a relationship with what each of the different this thing they're talking about. So we can, from this general formula, we can calculate, we can tell what the second alkane, the fifth alkane, or whatever structure would be. So if we are working with the third alkane, we can say this that would be C6H8, and for alkenes it will be C6H14, for alkenes it will be C6H12, and for alkynes it will be C6H10. So that's how we go about determining what the functional. We've talked about functional group, and also we've talked about the general equation, the general formula for the expression of such compounds. All right, I haven't spoken about a few of these topics that we'll be dealing with in hydrocarbons, in organic chemistry. Let's take this short break to evaluate what you have understood in this lesson that has been taught so far. Please, some questions will be asked, answer them, and we'll get back to you in a few. Welcome back. So, we've talked about what is organic chemistry. We've talked about some organic terms in organic chemistry. We also made mention of some of the characteristic features of organic compounds, but I want to emphasize on some specific characteristics features of organic compounds. Organic compounds are majorly known for certain features. They possess some unique characters, and such characters include talking about their solubility, talking about their flammability, other structures, other physical properties as that. So I'll take it from the chemical part of it. They are joined by covalent bonds. The carbons, because of the carbons that it possesses, they are joined by covalent bonds, and the carbon bonds are attached to each other with a very strong force. The amount of energy required to break the carbon bond is about 364 kilojoules, and that's a lot of energy. So the bond that exists, the covalent bond that exists between the carbons, that is the intercarbon covalent bond, is a very strong one. But because it is a covalent bond, it simply means they cannot ionize in water, which means they will not allow the flow of electricity. Of course, they are not ions, they are just sharing. They are sharing the atoms, the electrons. They are sharing the electrons, so they cannot ionize in water. Hence, they are poor conductors of heat and electricity. Also, they are non-polar compounds. Generally, they are non-polar compounds, and they are insoluble in water. You find out that your petrol, your kerosene, when you pour it in, they don't dissolve in water. They are immiscible with water. And they are like because of the nature of their existence, they are joined together by by van der Waals forces. That is, each atom, each structure, each molecule is joined to the next by van der Waals forces. Also, they possess low melting and boiling points. This is as a result of the van der Waals forces. They possess low melting and boiling points. It can also be associated with covalent bonds, because covalent bonds generally have lower melting points than ionic bonds. The same thing applies to when they talk about their stability. They decompose at temperatures of about 500 degrees C. They decompose. They stop being whatever structure they used to be. They are very flammable. You can tell already. Your petrol, your kerosene, your diesel, you burn them, they produce a lot of carbon dioxide, that's carbon dioxide, after combustion. And their reactions are slower compared to those of ionic bonds. Of course, ionic bonds are all about giving and taking. They are about sharing. So they have to have a planning, a careful time to make such choices. Alright, we have a particular chemical structure on the board. I know this might be looking very scary to some of you, but it's just a combination of carbons and hydrogens. And interestingly, I decided not to make it too complex by not adding halogen family members into the structure. But you find out that to name this structure is actually very simple. So I want you to try it out. Let's see if you can actually get what the name of the structure is. So just take some time out, think. So I'll wait for you while you think. Yeah, try to name this particular structure. Alright, so what name do you have for this structure? Okay, let's see what the name of the structure really is. How do we go about naming any particular structure we come about? Well, there are some things that we should need to keep at heart. The first thing is this: what would be the root name of the structure? The root name of the structure. The root name of the structure is always determined by the longest continuous chain. The longest continuous chain. Now, that root name is what some of us do classify as how do I call it now? The homologous series. We'll talk about the family name. That's what I would like to call it, the family name. Well, the root name also contains the number of hydrocarbons in the system. So this particular one will be very easy because I can see that all the carbons are joined together by single bonds. So you can actually come to answer that. This particular hydrocarbon is a member of the alkane family. Well, we'll understand that much better when we concentrate on that. So I said the longest chain. So you count continuous longest chain. It does not matter whether there is a bend or not. Many people would like to say 1, 2, 3, 4, 5, and we want to take it like that, but that would be wrong, because I could also take it as 1, 2, 3, 4, 5, 6, and that will still be wrong, because the truth is it can be 1, 2, 3, 4, 5, 6, 7. That's the longest continuous chain. 1, 2, 3, 4, 5, 6, 7. And of course, when we come across something as long as 7, we'll give it the name ept. Of course, we will come to talking about structures where we have met. For 1, we have earth. For 2, we have prop. For 3, boot. 4, pent. For 5, eggs. For 6, ept. 7, oct. 8, non. 9, and the rest continue something like that. Yeah, we have deck. We have more than deck. So I will just simply because I cannot write everything, let's just take it like that. So for this particular one, we can count 1, 2, 3, 4, 5, 6, 7 as the longest continuous chain. So I already know it is an ept. And I have concluded that it is an alkane family, so I can say it is heptane. But it is not just heptane. There are still other things about it, other interesting features, because I've only considered the longest chain so far. I've not considered other chains, other connections to it. So it's time to consider other connections to it. And that brings us talking about suffixes and prefixes. Suffixes and prefixes. If you look at this is a mid name, this is a root word. But at the same time, even though it's the root word, it contains a suffix already, which is the tane. It shows it's a member of the alkane family. The ane here, I write it in cap locks. Ept, ane, this ane there, that's the suffix. It shows the family to which it belongs. So we will also come across certain structures, maybe something like, I'll draw something very simple. H, Cl, H. Something like this now. If I would like to name it, I would like to call this, of course, my longest carbon chain is 1, 2, 3. Agreed. We already know that. That's my longest carbon chain. So if I would like to name it, I would like to call this 1, 2, 3, says it is prop. And I'm having double bond between one of the two carbons. It will make me say, this is where I want to focus on. That's why I'm bringing up this kind of formula, drawing structure. Now, we number the carbon in the cases of other structures, such as ethane, butane. In case of the families of the alkanes, alkynes, alkanols, alkanoids. You name the position of their multiple bonds, so that we can know that it is at that particular place, at that particular location, that's where this particular bond is being formed. So this, of course, and when you are naming, you always name your bond. You number your carbon with your bonds in front. Even if your bond is actually at the back, you number from where your bonds is being made, where is closest to your bond. Peradventure, this was something like C, and I'm having H. Of course, I've changed it from prop now. It is now 1, 2, 3, 4, 5. It's now pent. In this pent, I am not allowed to count 1, 2, 3. I have to count 1, 2. So this is going to be my carbon 1. This is going to be my carbon 2. So I would name it pent 2N. Now this N is showing the family it belongs to. Just like this N here is showing. It's telling me it is a member of the alkane family. Is a member of the alkane family. So I can continue naming now. I think I've emphasized on my point about the suffix. Now let's go to the prefix. The prefixes show other compounds that are in the particular structure. It shows other compounds that are in the particular structure. For example, in this particular structure that we're looking at, this is my first structure. I'm coming back to it. I can see I've labeled 1, 2, 3, 4, 5, 6, 7. So I want to mark them as gone, 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 and gone, so that I can see what is left. Oh yeah, now I can see I have this here. I also have this here. Of course, like we said up here, we label closest to our joints. And second thing again, we will also label such that you have the least number in your suffix. Such that you have the least number in your suffix and the least number in your prefix. Now, if it is not possible for you to have both together, then you must make sure that your suffix has the least number, then let the prefix carry a bigger number. You must first take care of your suffix before you care so much about your prefix. Now, if you don't need a number in your suffix, then you can go ahead and label it based on your prefix. So, in this particular condition, I could say 1, 2, 3, and I could say 1, 2, 3, 4. But 1, 2, 3, 4 will be wrong. It takes so long. I already have 1, 2, 3. So this is, I can say it is 3 is a methane, but it's not methane that we'll call it now, because it is not it's not complete. It is alkyl group. It's an alkyl group, so it is methyl. And here also I'm having another methyl, so I can say 3, 4 dimethyl heptane. Why am I having dimethyl? Because I'm having 2 methyls. So it is 3, 4 dimethyl heptane. Peradventure, I'm having 4 methyls. Of course, you know what you do. 3, 3. That's, I'm saying, depending on the locations, and you put the methyl and the likes like that. So here also in the up one, we can see our chlorine is there. So we have to label the chlorine too. The chlorine will be 2 chloropet 2N. Why 2 chloro? Because my chlorine is on the second carbon. If my chlorine happens to have been here, it would have been on the 4th carbon, so I'll have named it 4-chloro. If you are having just one, you don't need to put mono or anything. But if you are having more than one, you have to specify. Peradventure, I'm having 3 chlorines, just like CCl4. CCl4 is the most stable chloromethane. It is used as a refrigerant. It is used as a refrigerant. But when we want to name this, we simply call it chloromethane. That is in the general word. But when we want to specifically label it, we call it terachloromethane, because we have all the atoms, all the hydrogens of the methane is gone and has been completely replaced by chlorine. Tetrachloromethane. All the hydrogen is gone and has been completely replaced by the chlorine. So we call it tetrachloromethane. And of course, we could have a situation where we have more than maybe trichloromethane. Of course, does exist as well as other substances as such. All right. So basically, this is how we go about the naming of our compounds, the IUPAC standard. Now, there are other family group members that we should take note of. The family group members, family groups, are apart from the alkane and alkyl and the alkanes. So in a short while, you'll see all the family members on your screen. They should be on your screen about now. So we can see there the carboxylic group, the oic group acid, the carboxylic acid group, the oic acids, the alkanoids, and the rest of them. So those are the names of the functional group and their symbols. So let's talk about stereochemistry. Well, this aspect is going to be so loved by people who want to study industrial chemistry and biochemistry in the future, because you do a lot of things that have to do with this. And what is it about? Structures of chemical compounds. That's what stereochemistry is all about structures. So why are those structures? Why are these structures important? Well, let me start by saying this. The structures are important because they actually decide certain behavioral traits or certain characteristics of the chemical compound. There is a way in which a chemical compound will be connected to each other, as in the components of the chemical compound will be connected to each other, that one of them will be lighter than the other, even though they contain the same exact number of elements. They contain the same, maybe not lighter, but the bond between them will be stronger than the other. For example, in isomerism, that's the first part of this session. In isomerism, we see the existence of two compounds having the same molecular structure, molecular formula, but different molecular structures. Let's take an example. In isomer, and when we talk about two substances being isomers, it means that they have the same molecular formula but different structural expressions. Let's look at what we have down here. We have 1, 2, 3, 4, 5, and this should be called, and of course all of them are joined with singular bonds, so we should call it pentane, right? Good. We also have 1, 2, 3, 4, 5. We would have liked to call this pentane, but we can't call it pentane because it is not having a straight bond. But let's see. This particular one has 1, 2, 3, 4, 5 carbons. So we can say 5 carbons. How many hydrogens account from there, around, and back? So let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have hydrogen is 12. Let's come to this other one. How many carbons? 1, 2, 3, 4, 5. So we can say we have C5. How many hydrogens are ready? Let's go. I'll take it from here and around back to here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wow. So we can see these two different structures have the same chemical formula. They have the same molecular formula, C5H12, C5H12, but they are not the same compound. Then this is what the situation we call isomerism. Isomerism, where we have two different structures and they are giving us the same molecular formula. So what are the differences? What are the things that occur because of the way the carbon are connected to each other? We learned earlier that it takes about 400, almost roughly 400 kilojoules to break the bond between one carbon and the other. Now we have a chain for going like that, but here we have them strongly connected to one particular carbon. So there is a very, very high chance that this particular compound would less likely decompose compared to this. So to decompose this particular compound, it will require even more energy than what it will require to decompose this. That's one of the things that isomerism bring about. So how do we name this particular compound? What's our longest chain? 1, 2, 3. So we know it is a prop. And of course it is a member of the alkane family, so it's propane. And we have an alkyl, another alkyl, and these are methyl. So we have 2,2-dimethyl propane. So 2,2-dimethyl propane has the same formula as pentane. And that is the situation we'll talk about, we'll describe as isomerism. How about in certain conditions where there isn't even so much of this confusion as a totally different name? As in the case of what we have up here, we have two different structures that look alike. If you look at this structure up here, we want to write the chemical formula, we can easily come up with C2H2Cl2. Same thing here, C2H2Cl2. Some people would like to write the formulas as the elements come. You can simply call this particular one ClHC and then CHCl. And of course this one too will be ClHC, CHCl. So we are saying like it's the same thing, but these two substances are not the same. This is a situation where we talk about geometric isomerism. Geometric isomerism. In this particular one, the chlorine are connected in a cis manner. That is, one is up on one corner, the other one is down in another corner. In the other one here, we have both of them up. That's a trans connection. This is cis, this is trans. So this is even a form of isomerism, and it is known as geometric isomerism. So all these appearances, all these changes, all these minute changes that look like nothing, they actually go a long way to determining the characteristics of these particular compounds. Pentane is completely different from propane, and pentane always exists in almost liquid form. It is a denser liquid, denser gas. But propane is very light. It wants to just enjoy its life as a gas. And we are saying the same particular formula to express both of them, but different structures. So in stereochemistry, in our further classes on stereochemistry, especially when we get to the point of understanding majorly what these compounds, how they actually affect the strength of the bonds in future classes, we'll look at that and you'll see the importance of stereochemistry in organic chemistry. So let's talk about the classification of organic compounds. When we want to classify organic compounds, generally we classify them into two groups. We have some of them that we call the aliphatic organic compounds, that is the aliphatic structures. It's, of course, their classification is also based on their structures. When we say it is aliphatic, it means that their connection, when you draw the structure, you have them in straight lines. It may be curved, but it's always like a straight connection. There is always a starting point and an ending point, and the entire circuit breaks. But we have another group we call the aromatics. Yeah, the aromatics are actually round, circular. So it's like it starts at the point, it ends at the point it starts. It's not like the aliphatic where you start with an H and you end with a different H. In the aromatics, it starts and it moves around and comes back to the starting point, a circle. So we have about 3 different structures on the board. This one, let's start with this. This is 1, 2, 3, 4, 5, and we have 2 different alkenes. So we can call this 2 dimethyl. Sorry, 1, 2, 3. So 3, 3, not 2, 2. 3, 3 dimethyl pentane. And here we have 1, 2, of course this is, so we can call it 1, 2, 3, 4, 5, 6. We have, it's X in, but it is on 1, so X1 in. We have an habit when it is the 1, when this thing is on the 1, that is the suffix is on the 1, we usually do not specify. So if you specify, not bad. If you don't, it's acceptable. When it is on the 1, we usually do not specify. So you can call it hexane. Straight, without specifying. Alright, we also have another structure up here that we can actually call an isomer of hexane. Wow, lovely discovery. Please clap for me. I discovered another compound. Yeah, but I didn't discover it. I just found it, noted it. Well, this particular structure, if you look at it, it is moving round. The name of this compound is cyclohexane. Well, this is hexane. This is cyclohexane. They have the same formula. Well, why is this cyclohexane? If you check it out, you notice that it is the carbon bonds are all connected to each other, and they form a complete circle. The carbon bonds are connected to each other, and hence they form a complete circle. That's the first thing. Then why is it hexane? It is hexane because if we check all the connections, you will notice that it is all straight line, one joint, just the way our normal hexane have, just one bond connections between all the carbons. Well, we have a very unique one, usually drawn like this. Some like to do this. Some like to do this. And some still like to do this. Well, let me tell you this before we go on. This and this are not the same. They are not exactly the same. They do almost the same thing, but they are not exactly the same. It simply shows the arrangement of the structure inside, but this can be this or this. So let's forget about that for now. We are coming to come and talk about that in details in another class. So it is very important for us to note in classifying hydrocarbons, they can either be aliphatic, which says they are on straight lines, or aromatics. Okay, these are aliphatic. Not those. These are also aromatics. So when you're talking about the cyclos, cyclopentane, cyclobutane, cyclopropane, all of them are aromatics. And this structure is used to describe benzene. Actually, it is a cyclohexene. So we have benzene and the family of them. They are all aromatics. And we'll talk about aromatics in a few. We have been talking about organic chemistry and we're mentioning a lot of things. So, and every time I've been drawing structures and drawing structures, I've been drawing structures that contains carbon and hydrogen. Thus, we must have been talking about something very interesting, and that brings us to the matter of hydrocarbons. So, what are hydrocarbons? Hydrocarbons are substances which are made up mainly of carbon and hydrogen. They are made up mainly of carbons and hydrogen. So just like ethane and hexane and the other substances I've been drawing, you can have C12H26. This should be a 12 level 12 carbon alkane. So this particular 12 carbon alkane is just one of the compounds. It's also an hydrocarbon. Now, what are the sources from which you can get this kind of substances? What are their applications to our day-to-day life? What benefit are they to us? Are we supposed to eat them? Are we supposed to drink them? Oh, alkanes, hydrocarbons, generally can be found under the earth crust, and they are formed majorly from the decays, the remains of the decay, that is, the fossils of plants and animals, which have undergone serious pressure and temperature increase. That is, they have been compressed, they have been heated, and they have transformed, they have metamorphosed and formed a new substance. Oftentimes, we describe that substance as petroleum. So, what do we do with petroleum? Well, we use petroleum for many things. When we harvest, when we source petroleum from the ground, it is of very many use. But we cannot simply carry that crude oil, like we do call it crude oil. We cannot just carry it and pour it into our car engines and start going. No, there are some processes that it has to undergo. And one of these processes is what is called the cracking. Cracking of crude oil or petroleum. Cracking of crude oil or petroleum. What do we mean by cracking? Well, just like the name sound. Breaking it, snapping it into two. And how does this occur? Peradventure, you have this particular structure I wrote, this particular molecule I wrote here, and we would like to get two different components. We can crack it by heating it and subjecting it to special conditions, whereby it would decompose. Yes, I told you that hydrocarbons, organic compounds, they do decompose. Yes, it would decompose, and under a high amount of heat, this can decompose to give us C5H12 plus another C5H10, and it will give away CH2. CH4 in the process. The equation has to be balanced. It will give away methane gas. It will give away methane gas, provide for us pentane and peptyl. And peptine. It's give away methane gas, provide for us pentane and peptyl. No, this is not complete. I'll have 2. Yes, to give away ethane gas, provide pentane and peptine. Ethane gas, pentane and peptine. It will give away pentane gas, pentene and ethene. That's ethene. So this breaking away this thing using, of course, heat. And sometimes we use some chemical compounds to do this breaking, to do this cracking. And when we are using chemical, we call it carboxylic cracking. We call it carbonic cracking. That is, you are introducing a chemical into the substance to break it down. Of course, we can use heat, that is thermal cracking. So, apart from cracking of petroleum, when we crack petroleum, then we get this many produce. When we get this produce, this petroleum does not just give us the main produce that we need. It also gives us some other things that we call petrochemicals. And that's where this ethene there fall into petrochemicals. So what are these petrochemicals? They are byproducts, not the main thing we desired to get. The main thing we wanted in this place was pentane. We got it, and we got other substances alongside. So what are the advantages, or what are the benefits, what are the uses of these petrochemicals? Petrochemicals can be split into about, let's say 3. We have what we call the synthesis gas. The synthesis gas. The synthesis gas is one of the substances that is released. It is usually a mixture of carbon dioxide, water vapor, and carbon monoxide, and of course it is usually charged with a lot and lots of energy. It is charged with lots and lots of energy. It is brought about due to the decomposition of some of this great petroleum produce. So when it comes out, we do find a lot of use for it, and some of the uses are they can be used in the making of explosives. Yeah, war, right? No, but not only war. We can also use them as petroleum additives to make our petroleum cleaner, to make our fuel engine burn. To make our fuel burn better. We use that also as petroleum additives, and they can find use as refrigerants. Yes, they are also being used as refrigerants. Okay, we also have the alkanes. Alkanes, of course, if you look at it, we see there's always an alkane. There's the ethene. There will always be a member of the family there. Yes, just like the name sounds. I don't know if you have noticed, there is something called polythene bag. Yeah, polythene. I think if you just create a little space between there and you put an E, looks like something familiar. Polyethylene. So that's one of the uses of some of these chemicals. They are used in making nylon bags. They are used in making cosmetics, even synthetic rubber. We can use the members of the alkene family for these particular purposes. And we also have the aromatics. The aromatics. Now, there is a chance that this particular structure that we have here, that we are simply calling a pentene, it might actually not be a pentene. It might actually be a cyclopentane. Remember that the chemical formula of a pentane, of a cyclopentane, is identical to that of the pentene. So it is actually possible that this is actually a cyclopentane. pentane. So, but then, what are the advantages? What are the uses of these aromatics? They are also used in the making of plastic bags, in the making of plastics that we carry in our houses, in the making of detergents. They can be used as refrigerants. They have very many uses. They have very many uses. So these petrochemicals, when we undergo the cracking process, it is not a destruction or a wasteful act. It is a process. If it is rightly done, every single thing that comes out of the cracking process is valuable. Everything. All right, let's take a look at the first group of the hydrocarbons as we continue. Let's talk about the alkanes. The alkanes are the ones that have no double bonds, no triple bond. All the carbons are connected to each other through single bonds. All carbons are connected to each other through single bonds. They may possess hydrogens in other bonds or other compounds or other elements. But all the carbons are connected to each other via single bonds. The general formula, that is the family formula, is CnH2n plus 2. CnH2n plus 2. How does this formula come about? If you look at this, you see there are C's, 1, 2, 3, 4, 5, 6 C's, and on each of the C's there is an arrow up and one down. So that tells us how many H, and we still have this extra one and this last one at the ends. So that's why we have CnH2n plus 2. So our first member of the family is methane. That's methane. Methane, of course, using this formula, that's our N is 1, that's C1. Our H is going to be 1 times 2, that will give us 2. 2 plus 2, that will give us 4. So we'll simply write it as CH4. That's methane, CH4. So let's talk about methane as our element of discussion, as our subject of discussion. Methane can be produced in the laboratory by reacting a salt, which is the sodium ethanoic salt, with sodium hydroxide. Reacting sodium ethanoic salt with sodium hydroxide, and when we react it, what we would have is sodium carbonate, that's sodium trioxocarbonate 4, and methane gas would be liberated. Let's discuss more about methane. What are the physical properties of methane? Methane is a colorless, odorless gas. It's slightly soluble in water. It is less dense than air, and it is neutral to litmus paper. It is neither acidic nor basic. Chemical properties of, in fact, not methane alone, but all the members of the alkane family. Well, all the members of the alkane family, when they react with air, when you burn them in air, they will simply produce steam and carbon dioxide. They will produce steam and carbon dioxide. Of course, that is in excess air. But when the air is very limited, they find their own way. Except they don't react completely, they will produce steam and carbon dioxide at least. So in excess air, they produce steam and carbon dioxide. And very, very good to note, when you engage them in chemical reaction, when you force them to engage in chemical reaction, they only take part in substitution reaction. Why do they do that? Because if you check out, all the chances of the element, of the substance reacting with another particular element has been blocked. For it to react, it has to give away at least one hydrogen for something new to come in. Maybe sodium. it has to give away one hydrogen for a new thing to connect. So it's only they all only react with substitution method. If it is not substitution, they will not react. Now methane reacts with chlorine on a very special condition in the presence of ultraviolet light. Ultraviolet light serves as the catalyst of this particular reaction, and this reaction is a 4-phase reaction. I wrote the very first phase here. That's methane reacting with chlorine to produce HCl, that's hydrogen chloride gas, and methane chloride. When you take this methane chloride, methyl chloride, chloromethane, sorry. When you take this chloromethane and you react it with chlorine again, it will produce another HCl plus dichloromethane. When you react it again, it will produce what we know as chloroform. Of course, HCl will always be produced at every stage. Trichloromethane, which is also known as chloroform. And if you make it react one more time, it will produce the most stable of all the chloromethanes, which is CCl4. That's tetrachloromethane. So what are the uses of the alkane group, the alkane family? Methane especially is used as a fuel alongside with very many of the compounds of the alkane family. They are used as fuels. They are burned, and their end product is always, as I said, steam and carbon dioxide with lots of energy. They are exothermic, so they release lots of energy. So they're used as fuels, and also you can find their application in the preparation of hydrogen, carbon dioxide, and many other substances like that. Chemical reagents that can be useful in the laboratory, that can be used as a drying agent, as cleaning agents, even in the production of tetrachloromethane and chloroform, which actually have important uses in the laboratory. Let's talk about the alkane family. The alkenes, they have the general family notation that's CnCH2n. If you look at all the alkanes, you discover that there is always something common to them all. They always have this connection, double bond. You'll find that particular double bond on one of the particular locations. It might be, you might have C's everywhere. You just find it in one place. Now, this is what makes them very, very unique. What makes them into that particular group. Now, if this double bond were not to exist, they would have had the opportunity of carrying one hydrogen. So, as against the first group that had that +2, those 2 hydrogen that they would have held were removed and replaced with a second bond that joins the carbons to each other. So that's how the alkanes exist. That's how they form their own structure. Generally, alkanes, if you check them, you find out that their first 4 substances, that the first 4 of them are gases. The next 13, that is from the pentane to the 17th alkane, they are liquids, while 18 and above are all solids. They exist in solid state naturally. So, how do we produce ethane? The very first member of the group is ethane. Of course, it cannot be methane. Why can't it be methane? A double bond cannot exist if there is no second carbon. There must be a second carbon to connect the second bond to. So it's not possible for there to be a methane. So the very first member of this group is ethane. Ethane. So let's talk about ethane. How do we produce ethane? Industrially, by cracking, of course. When we crack the 17th compound, we'll get the 8th compound, and we'll get ethane, 3 molecules, and we'll get, if we crack the 17th alkane, we'll get the 8th alkane, we'll get the ethane, it's 18, and we'll also get propane. So what we need here is the ethane. Also, we can also get it by simply drying the ethanoic acid. How do we dry the ethanoic acid? Of course, we know that H2SO4, concentrated H2SO4, is hygroscopic. That is, it loves water. It absorbs moisture from the environment. So if you bubble or you pass it through, it would extract out the water from it and leave just the ethane, which will come out as a gas. So these are the ways to prepare ethane in the laboratory. What are the features? What are the characteristics of ethane? Physically, ethane is colorless, but it has a faint, sweetish smell. It is sparingly soluble in water. It is sparingly soluble in water. It's almost insoluble. It is less dense than air. Of course, if we look at the chemical structure and we do the addition, do the math, we'll find out that it is less than 28.6 in terms of its mass. That's taken as the approximate 28.8 something, 28.92. Yes, 28.92. That's the approximate mass of air. And this is just about carbon dioxide, carbon and hydrogen. That's for hydrogen. That's about 20. So it is less dense than air, and it is neutral to litmus. It is neither acidic nor basic. Now let's look at the chemical combinations and chemical properties. It reacts with oxygen. That is, in burning process, it combusts and it produces water and carbon dioxide. Of course, the water, there is steam because of the amount of heat that is involved. It takes part in addition reaction. Yes, it takes part in addition reaction, and most of its addition reaction includes its reaction with oxygen, reaction with halogens, reaction with hydrohalides, and also reaction with manganese 7 it's a tetraoxomanganate 7. Tetraoxomanganate 7. Now, all these reactions involves it deciding to lose this double bond and behave like an alkane. Now, when it loses this double bond, it now connects to all these substances in its addition reaction. That's how we say it takes part in addition reaction. After it has taken part in an addition reaction, it may also now later take part in substitution reaction. That is, what products might have come out of it can also take part in substitution reaction. And if there is need for it to substitute an hydrogen during the same addition reaction, it would also do same. So it also engages in what is known as polymerization. So what is polymerization? Polymerization is the opposite of cracking. It is a situation where two molecules or more molecules that of lighter elements or lighter compounds come together to form a larger compound. When two elements or two substances, two compounds of lighter elements or lighter compounds, two lighter compounds come together to form a bigger compound. For example, you have your ethene coming to react with maybe propene, and then they form a bigger structure of C5H10. Now, for this reaction to occur, this one comes with C double bond C and the rest is occupied. The other one comes with C double bond C, C, and the rest is occupied. Now, when they are about to connect to each other, this one will lose its double bond and have an hydrogen here. This one also will lose its double bond, and then the two of them would combine of course the hydrogen that is supposed to be on one of the edges will join, and then you have 1 2 3 4 5. Oh, sorry, this one will lose, this one will maintain its distance, this one will lose its double bond and use it to connect to the ending of this, that's this side. So we'll have something like C. So the hydrogen that was supposed to be here will move, and then we'll have our structure will be H H H H H H H H H H. So that's the way in which it reacts. So what are the uses of ethane and the alkene family? Generally, they are used in preparing important organic compounds, especially ethane. It's used in the preparation of very important organic compounds. It's used also in the, it's used in the production of PVC. That's polyvinyl compound. It's used in the production of PVC. It's also used in the production of polyethanes. That's polyethylene bags. It's also used to make synthetic rubber. Yes, in production of synthetic rubber, we use alkanes. Alkanes find their use in production of synthetic rubber, as well as the production of petroleum additives. And also, we use ethane specifically also for ripening of fruits. So, you see that this just singular compound, ethane, has a vast number of uses. Let's go ahead and look at the alkyne family and we can proceed. So, coming to the alkynes. The alkynes, of course, their formula is there. CnHn, 2n rather, minus 2. CnH2n minus 2. They are identified by this distinctive 3 bonds, that's triple bond existing between 2 carbon atoms, as what are indicated here, as in the case of the first of its kind, which is the ethyl. The ethene. So, how do we prepare this in the laboratory? Simply by reacting calcium carbide with water. Calcium carbide with water, and to produce calcium hydroxide and your ethene. So, what are the physical properties? Physical properties include, it is a colorless gas, it has a sweet smell when it is pure. Yes, it has a chance of reacting with air very, very fast. So, it is likely not to exist in its pure state. It is sparingly soluble in water, slightly denser and less dense than air. It is unstable. It is unstable in all its ways. And why do we say it is unstable? Because it should only be let to stay in its gaseous form. If it is compressed, even some of its liquid, some of its higher compounds, when they are compressed beyond certain levels, they could explode. So they are very, very good for making explosives. Bravo to them. Now, we have a way of detecting how to convert them into explosives. I'll tell you how to make one explosive today, but do not try it at home. My own advice. Alright, let's continue. Let's look at the chemical properties. The first chemical property we'll look at is the combustion. It is combustible. Yes, it is combustible. Just like every other hydrocarbon, you can burn it in the presence of air, and when you burn it in the presence of air, it will produce, as usual, steam and carbon dioxide. Yes, it partakes in addition reactions. It partakes in addition reactions, and very many of its addition reactions involves it adding hydrogen, adding halogens and other substances. The first thing it does when you want to partake in any addition reaction is to first let loose of one of its triple bonds. Then the next time it partakes in the reaction, it will let go of the second of its triple bond, and then it will become like an alkane rather. It will become like an alkane. Now, all these double bond, triple bond, of course, we talked about it earlier, that it leads to what we know as the structure being unsaturated, So we have a way of testing for the saturation of a particular compound. And how do we test for it, whether it is saturated or not? To test it, you simply pass the hydrocarbon through bromine water. Bromine water is reddish brown, but when you pass an hydrocarbon that is unsaturated through it, it becomes colorless. Yeah, it will look like a miracle. Yeah. And also the same thing happens to it when you pass it through potassium tetraoxomanganate 7. When you pass it through potassium tetraoxomanganate 7 also, it will become colorless. Yeah, another miracle. So let's go ahead and look at other reactions that this particular interesting compound undergo. It can undergo substitution reactions. Yeah, it can give away its carbon to copper. It will react and it form hydrochloric acid with copper carbide. It also does the same thing with silver. It will also do exactly the same thing to form an acid and the carbide of that silver carbide. Now this silver carbide or copper carbide is explosive. They are solids, but they are explosives. Now peradventure you happen to know somebody who created such an explosive, and you are asked to come and deactivate the explosive. Well, there is a cure for it. All you need to do is to bubble or react it with concentrated hydrochloric acid. Well, that's also dangerous, hydrochloric acid. Now when the hydrochloric acid, I'm sorry, I said hydrochloric acid, no, I meant H2SO for that, tetraoxosulfate 6 acid, which is also very, very, very dangerous. Now the tetraoxosulfate 6 acid will react with the compound and form the copper salt of tetraoxosulfate 6, that's copper tetraoxosulfate 6, and it will liberate the ethene gas. So it also engages in polymerization. Yeah, its own polymerization is very interesting. You can see what I have here, a formula. 3 of it reacting to form a structure like of something like benzene. So actually it could form benzene or a complex polymer as that. So what are the uses? What are the uses of ethanes or alkenes generally? They are used as fuels. Alkynes generally, they are used as fuels, especially for lighting lamps for miners in the mines. They use them as fuels. Ethane is used in for welding. You see, these people, they say they carry they don't go and buy welding gas. That welding gas, there are 2 tubes. One of it is oxygen, the other one is ethane. Yes, when it is mixed with oxygen and it is set ablaze, it burns at about 1,500 degrees Celsius to up to about 3,000 degrees Celsius. That's to the extent it can melt iron. It can even melt steel. So it can melt the compound and we can use it to join, of course, while it is in the liquid form. It can melt substances. It is also used in the preparation of very many chemical compounds. Very many chemical compounds. And when you polymerize it, yes, when you polymerize it, you get substances like plastic, like synthetic fiber, like even artificial rubber. You can get it out of your ethane. That is when your alkynes, let me put it that way, because it's not only ethane that can be polymerized to get some of these substances. When you polymerize your alkyne, you get your rubber, your synthetic, your rubber, your plastics, even some synthetic fibers. So these are some of the benefits of alkynes. So let's go ahead and talk about the aromatic hydrocarbons. Since we talked about them, we said alkynes can blend together to form something like an aromatic hydrocarbon. So let's go ahead and look at aromatic hydrocarbon with more concentration on benzene. So we want to talk about the aromatic hydrocarbons. Like we said earlier, we said aromatic hydrocarbons simply talk about hydrocarbons which form rings. Rings, that is, if you draw this connection, they always form circular shapes. but we are focusing more on benzene because it's a very unique one of them. It is we look at benzene, it has a chemical formula C6H6. When you first look at benzene, you see something like this: 2 carbon bonds, 1 carbon bond, 2, 1, 2, 1. But when you take a look at it at another point in time, you see it like this: 1 carbon bond, 2, 1, 2, 1, 2. So we discover that the benzene molecule does not remain in a particular shape. It's like it is rotating, and the carbon bonds, the double bonds are shifting, and the single bonds are shifting. So we simply represent benzene with this symbol, where we draw the hexagonal shape and we just put a circle within to tell us that the double bond and single bonds are shifting positions. All right, when we look at benzene, benzene is a colorless liquid. Physical properties is colorless liquid. It is sweet smelling. It's insoluble in water, and it has a boiling point temperature of 80 degrees Celsius. It partakes in substitution reactions. That is, it would either lose 1 carbon and 1 hydrogen to get something else to replace it, and it partakes in one particular ridiculous reaction. That is in the production of what is known as cyclohexane. Something that looks like it's still a circular bond, but it will lose all its double bonds, and instead of it just partaking in substitution reaction, it will actually add to itself. That is, it will partake in an addition reaction under the special condition that nickel will be there present as a catalyst, and the temperature of about 180 degrees Celsius. 180 degrees Celsius. All right, we can find it partaking in substitution reaction such that it will form phenol, where it will have hydroxyl added to it. It can form toluene when it has methyl added to it. That is, methyl benzene is known as toluene, and when we have dimethyl, that is dimethyl benzene, is known as xylene. All right. What are the uses of benzene? It is used in the production of certain compounds that are needed in the production of nylon. It is also used in the production of certain compounds. It is used in production of compounds that are needed for production of industrial materials, such as nylon, such as pesticides, such as explosives, plastics. Talk about detergents, dyes for making dyeing clothes, even medications, drugs that are being consumed. Some of them contain benzene in their making, or some of them, their products, the products that are used in making them are produced by use of benzene. So we see that even the aromatic hydrocarbons are of very great importance. Let's quickly consider the alkanones, that's alcohols, and we'll see some of their uses before we come to an end of this particular lesson. All right, let's talk about the alkanones, or what I would like to describe as the alcohols, because that's what they contain majorly. Oh yeah, this group, the general family group formula of CnH2n plus 1 OH. So that's how we know them. They contain the hydroxyl function. When you draw them, when you draw their structure, you have something like this. Now, whenever you see R is simply representing the alkyl group. You saw that when we showed the homologous series, that the R always represents the alkyl group. That is, it's unique. It is a unique thing that changes in every of the substances. That is all our formulas. So our RAX is part of the alkyl. It shows the remaining part of the formula. So as we're saying, we have alkanones can be of 3 different types. We can have the primary alkanone, which contain hydrogen, and an alkyl group, of course, which will be counted with this alongside to form the complete name of the alkanone. We also have the secondary alkanones, which actually have 2 different alkyl groups. So we just count this particular alkyl group alongside with this other alkyl group, and we count on. Now the thing about this is the alkyl groups are on two different, so it will most likely be even denser, because the carbon will now form on, not on the first, the alkanone, the all will no longer be on the first of the distance. It will now be on either second or third, depending on what number the carbon falls on the smaller of the two alkyl groups. And we also have the third, that is the tertiary level. At the tertiary level, we have 3 different alkyl groups. So it can actually be even more complex. We have to now check the 3 alkyl groups to decide where our ore will fall. All right, let's look quickly at the ethanol, which is the first member of ethanol. Actually is not the first member. Methanol is the first member. Methanol, it is actually poisonous. It is not edible, that is, it's not consumable. So it is poisonous. It's known as wood spirit. But we have ethanol, which is a consumable one, and it is generally known as alcohol. Yes, alcohol. Well, how do we produce alcohol? We produce alcohol via a process known as fermentation. For industrial purpose, we produce it through a process known as fermentation. How does this fermentation process go? You take your starchy food, either your barley or your starchy food. It should be in the granulated form, because reactions are slower reactions are faster in granulated form. Take your barley food and react it with certain reagents, ranging from your maltase. It will go through your maltase stage and then eventually find itself in the glucose stage. And at that glucose stage, it should be left and allowed to ferment. Some reagents can be added to hasten this fermentation, like yeast. Now, when this fermentation occurs, your alcohol will be produced, which is ethanol, and carbon dioxide would also be produced. So the reaction will end up producing ethanol and carbon dioxide. What are the physical properties of ethanol? Ethanol, it is a colorless volatile liquid. So if you actually leave it open, it tends to evolve. It tends to vaporize very quickly. Even when you take it, when you put it in your mouth, you get this kind of feeling of evaporation occurring. It is readily soluble in water. So when you mix it with water, it's soluble. Just like your medicated spirits, you pour it, you feel the coolness, and it is just vaporizing. That's why you say it is volatile. It vaporizes so quickly. Also, it has a characteristic taste and smell. Yes, it has a characteristic taste and smell, and it is neutral to litmus. It has a boiling point of 78 degrees centigrade. Also, let's look at the chemical properties. Chemical properties are it's combustible. You burn it in air, as usual, as all hydrocarbons. It produces water vapor, that's steam, and carbon dioxide. You can react it with sodium, and it will liberate hydrogen. If you react it with iron metals, it will liberate hydrogen. Metals are in the electrochemical series. It will liberate hydrogen. You can also react it with the compounds of sulfur chloride, phosphorus chloride rather, the compounds of phosphorus chloride, and to give chloroethane. Of course, it will also liberate hydrogen chloride gas. Yes, when you also react it can be oxidized using potassium heptachromate 6. Potassium heptachromate 6. So that's potassium heptachromate 6. That gives the oxygen, and it liberates ethanol and, of course, steam. And then this also, it takes part in what is known as esterification. All right. Yes, it can also be oxidized. It can be oxidized, and when it is oxidized, it will be oxidized using potassium heptaoxochromate 6. Potassium heptaoxochromate 6. That's this particular expression here, and when it is oxidized, it will liberate ethanol, that's this compound here, and give off some steam. That's water vapor. Also, it can react with ethanoic acid or methanoic acid or any alkanoic acid. That's one of the interesting reactions of the alkanols. They react with alkanoic acids and they produce alkanoates and water. So this is our alkanoate is a reversible reaction. Our alkanoates are usually described as esters. They are called esters. So this reaction is called esterification, the production of esters. All right, what are the advantages? What are the uses of the alkanols? The uses of alkanols. One, they are generally used as solvents, since they exist in their liquid forms, and they are the solvents of organic compounds. So they are used as solvents for dissolving organic compounds. Yes, you can use them as solvents generally. You can also use them as fuels. They are used as fuels. They are used as anti-freezing agents. They are in vehicles, especially engines, since the freezing point of alkanols, ethanol specifically, is about minus 154 degrees Celsius. Minus 154 degrees centigrade. It will not freeze until this point. So it can prevent freezing of your petroleum products in your engine. So they are used as anti-freezing agents. They are also consumed as drinks. Your beer, your wine, all these substances contain certain quantity of ethanol, and they are used as raw materials for producing important materials such as esters, which are known as our perfumes, such as alcohol. They are used even as for treatments. They are used in production of some important chemical compounds as well. So that brings us to the end of this particular lesson. But before we go, let's quickly take a quick recap. We looked at hydrocarbons and we talked about organic chemistry. We talked about organic chemistry. We said, what is organic chemistry about? Organic chemistry simply looks into the chemistry of carbon. And we talked about the characteristic features of organic chemistry in terms of solubility, which is they are insoluble in water. We talked about their polarization, that they are non-polar substances. We talked about the fact that they have generally low melting and boiling points. Let's go to the terms. We talked about the homologous series. We talked about the family name, the family formula, and the likes of them. We also looked at the IUPAC method, the IUPAC nomenclature pattern, how IUPAC names the aliphatic hydrocarbons. We then talked about chemistry, stereochemistry, where we said that it's all about structures, the structures of compounds, where we also discussed isomerism and geometric isomerism. We looked at the classification of organic compounds into aliphatic compounds, which are on straight lines, and aromatic compounds, which forms rings. We also talked about the hydrocarbons, that is the different types of hydrocarbons we have. Petroleum produce are the kind of products that come out of them. We also talked about the alkane. The alkane, we're having the formula CnH2n plus 2, which methane is the first family member. We talked about the alkenes, which have CnH2n with ethene being the first family member. We talked about alkyls, which have CnH2n minus 2, which has ethine being the first family member. We also went to talk about the aromatic hydrocarbons, that is the hydrocarbons where we focused on benzene. We looked at the structure of benzene and how it exists, the kind of reactions it partakes in. We then looked at the alkanols, where we mentioned that methanol is the first family member, which is poisonous, not consumable, but we focused more on ethanol, which is the second family member, which can be consumed as drink, and many of its uses and application. All right, having talked about so many things in this particular lesson, I hope that you'll be able to give very, very good results in this coming quiz. In a short while, some quiz will be displayed on your screen. Please attempt them, and if there is any of it which proves to be problematic, you can go over the video another time for